good about you know, the rhythm and everything last time, so I wanted to very quickly go through, of course, not the proofs, but just you know the sequential, you know, just page after page. So you remember we defined the notion of amplification. So this operation on II1 factors of amplification by real numbers, that was one thing. The fundamental group. We also introduced the this class of semi-finite von Neumann algebras. We defined what that is. And to infinity factors viewed as infinite amplifications of II1 factors. And we also emphasized that you can obtain such semi-finite von Neumann algebras with rather canonical semi-finite traces through the so-called basic construction. Okay, so that's comes from an inclusion of finite von Neumann algebras. So when D is in M, an inclusion of von Neumann algebras, you can construct this new algebra, bigger algebra, by adding to M the orthogonal projection of L2M onto L2B. That's the so-called basic construction, and this is in semi-finite von Neumann algebra with a rather natural trace TR, okay, which we defined. Then we clarified what are all the von Neumann representations, or if you prefer, Hilbert M modules of II1 factor. So they are classified by the dimension, the relative dimension of the Hilbert module, the dimension over M of the Hilbert module, okay, which we defined, and we showed. I suppose, I hope, in a rather convincing manner, this theorem, which we didn't really give details, but it's right. So this part, the first part of representing any Hilbert module as a sum of such cyclic modules of this form, L2 of MP. So you see where it's obtained by hitting on the right with projections. So these are sort of generic in the sense that any other Hilbert module is obtained by direct sum of these. And the dimension, the Hilbert dimension, the dimension of the Hilbert module is just the sum of those, the traces of those projections, okay? So this formula here. And so this is all very intuitive. It's very much related also with the amplification of II1 factors. You can also obtain all Hilbert modules of M by cutting appropriately amplifications L2 of amplified of M. And then we also introduced some more classes of II1 factors. We defined more classes. So the group von Neumann algebras associated to a group, to discrete groups, which will be factors exactly when the groups are infinite conjugacy class, ICC. And then we also introduced this other class of partial von Neumann algebras and II1 factors from group actions. So measure preserving actions of groups on probability measure spaces. Okay, so that's a cross product type construction, and I gave you that, sort of more intuitive, hands-on description of that as an algebra of Fourier series formal series is like this, with coefficients in L infinity of x, and this so-called what I call well, one calls them the canonical unitaries, or you can view them as indeterminates, okay? In this, like the monomials in the algebra of Laurent polynomials. Okay, and when the group action is free and ergodic, this will give you a II1 factor, and then infinity of x sits in here in this group measure space II1 factor as a maximal abelian algebra with the normalizer, since it contains, of course, all the UGs and also the unitaries in L infinity of x, which obviously normalize it as well. So together all this will generate this algebra as a von Neumann algebra, and something like this is what one calls a Cartan-Seb algebra. We'll get back to that with a more sort of abstract definition. Okay, so it's like a diagonal, right? That's the idea of the group measure space. So this maximal abelian is like a diagonal around which, you know, all the algebra turns. And one can build more factors through this series of operations. Let's not stop much on that. Now, we kind of said that it's pretty easy to prove this theorem of Mara and von Neumann, that the hyperfinite II1 factor is the unique approximately finite dimensional II1 factor. In other words, any II1 factor that's approximately finite dimensional in this sense here, and which is what one requires, of course, some separability condition, okay? Either that you require that M is separable, or what's equivalent with it's countably generated as a von Neumann algebra, then it's isomorphic to the hyperfinite II1 factor, okay? This is really a very, very useful exercise, and I try to convince you that it's not much more difficult than proving this result in the abelian case, the uniqueness of the diffuse abelian von Neumann algebra, separable abelian von Neumann algebra. Okay. And then that, of course, in particular shows that the fundamental group of the hyperfinite one is all R plus, because it's very easy to see amplifications of AFDs, AFD. Okay, and now the thing we tried to do next was to introduce a notion of amenability for von Neumann algebras. To that purpose, I reminded you first the definition of an amenability for groups. What do I have in mind? I wanted to prove, to give a completely abstract characterization of the hyperfinite II1 factor. Like, you know, the hyperfinite II1 factor is unique II1 factor with these properties, but not in this kind of, you see, when you say AFDs, it's already kind of, I would not view that as an abstract characterization, right? Because it's like you already, you know, say almost everything about it. So now, if, so it's more like a property, a functional analysis type of properties. So that's what we would like. And I'll explain why that is very important, okay? So that's something that I missed, I think, to do yesterday, and I wanted to get back and emphasize this a bit more. So this is the well-known, I suppose you actually knew, all of you, the definition of amenability for groups with the existence of invariant mean, for Neumann's definition. By the way, the name amenable was not given by for Neumann. We used another term which now I cannot remember. Anyway, so okay, and for Neumann algebras we will introduce this as a definition of amenability, or rather for threshold for Neumann algebras. Remember, with by requiring the existence of a similar kind of invariant mean, like for groups, so something that we will call a hypertrace, okay? So you notice it's a very strong analogy, right? Very strong analogy. And actually, just from this, you know, it's more than an analogy, it's really a properly defined property, in that, you know, whenever we have, say, if you have a property for that you want to pass from groups to the group for Neumann algebra, you would like that property to happen for the group if and only if it happens for it's for Neumann algebra, okay? And that requirement is satisfied here. Indeed, you have that L of gamma is amenable if and only if gamma is amenable. And the proof was not difficult. We gave it in full details. This was one implication, and then, you know, this was the other implication. I wanted to, it looks like here, you know, in this definition, we are a little bit hooked to this so-called standard representation of M on L2M, okay, the representation of L2 on L2M, the one associated with the trace. Okay, I never mentioned it, but that's what one calls L2M, is what we call the representation of M here by left multiplication. That lambda representation, lambda is one calls the standard representation of M. And so this result here, I didn't even call it a theorem, it's very easy to prove that you actually requiring that existence of the invariant mean for that representation is equivalent to having it for any other representation, and having it for all, therefore. And due to that, you can you deduce, it follows that if an algebra, threshold algebra for Neumann algebra is amenable, then all its subalgebras are amenable, right? And so, like for groups, by the way, if a group is amenable, all its subgroups are amenable. Now that comes from this part, which says that if you have a von Neumann algebra that's generated by, I mean, yeah, well, with an amenable subalgebra, so if M is a threshold for Neumann algebra with a subalgebra B that's amenable, and you have unitaries in M that normalize B, and a group of unitaries in M that normalize B and it's amenable, that group, so it's like a representation of an amenable group, okay, then the von Neumann algebra generated by those unitaries in B is amenable. So this proof is absolutely, proving this is basically identical to this proof here, okay? So that's why I said this as a corollary to this proof, to this part of the proof. Okay, so that obviously gives you, so it's this page that I was missing and wanted to, you know, kind of get back and you know, put these kind of very concrete examples of amenable groups and amenable von Neumann algebras, and comment a bit more on that. So first of all, you know, what's trivial already, you know, with this basic definition. By the way, in the next pages we have the Fellner condition for characterizing amenability. But even without that, you see immediately from the definition of amenability that locally finite groups, in particular finite groups, are amenable, that the abelian groups are amenable. That's because you can construct easily an invariant mean by averaging over bigger and bigger squares, okay, in the case of Z over intervals, okay. And also for when you have a short exact an exact sequence, so gamma is a cross product of H with gamma 0 by some cocycle. So, well, when you have this a normal group, this is a quotient of that. And if this gamma will be amenable if and only if these two are amenable. Now, this actually, you know, in principle, at least probably one of the implications would require, you know, having also this Fellner condition, which we will get to, you know, on the next page. But, you know, let's already mention that here, that you get, because of this machinery, you know, you get lots of examples, in particular, for instance, these read products, where H and gamma 0 are amenable. This read product will always be amenable, because, you know, this is, you remember, H to the power gamma 0, I mean direct sum of H gamma 0 many times, with gamma 0 then acting on it by the coordinates by translation, okay? For instance, you can take H finite and gamma 0 Z, okay? Look here, that's what I was doing here. Why would that be interesting? Because we actually would like to have ICC amenable groups, because that will give me amenable II1 factors L of gamma through the group for Neumann algebra construction. And for that, you know, we have S infinity as an example, but these are, you know, very easy to see that they are ICC whenever the group gamma 0 is infinite, of course, and H is non-trivial. Okay, so for instance, all these groups will be ICC amenable. Okay, so now this was very upsetting. I was very frustrated when I realized that I did not discuss the amenability of R. So we proved that any amenable to one factor is, you know, must be isomorphic to R, but perhaps you have, what about, you know, to start with, why is R amenable? And that's very easy to see, because you remembered how we constructed it from this dense subalgebra, the tensor, infinite tensor product. Clearly here, in the unitary group here, you know, this 2 to the n by 2 to the n matrix algebras larger than larger, if I take the unitaries with all entries plus minus 1 or 0, which means automatically you have just one non-zero on each row, I mean plus or minus 1, therefore, on each row and column, okay, that this will generate this as an algebra first, and then, you know, therefore the whole thing as a von Neumann algebra, okay? And this group is locally finite. So we generated it with this locally finite group, and you remember the corollary on the previous page with this proof. I mean, there was this is a, you know, very strong result. I mean, this technique here, because, you know, it allows you to give this many examples, and here is, for instance, one application is that this will give you R as a, I mean, show the amenability of R. Okay? Now also, of course, abelian for Neumann algebras are amenable. Any group measure space for Neumann algebra is amenable once the acting group is amenable. again, you know, because of the corollary on the previous page. It will be an amenable II1 factor if the action is free and ergodic in addition. Okay, so then we proved so that was those pages I inserted them, okay, they were new pages. Now this was Fellner's condition, which we proved, and then the reason I wanted to prove that in detail is really because I was following exactly that same proof to prove Kahn's Fellner type characterization of amenable II1 factor. So that's exactly actually this and the proof are from his paper, okay? So he proved on the one hand that you know you have the existence of the hypertrace, which I'm calling amenability for the von Neumann algebra to be equivalent to this Fellner type condition on the one hand, okay? And the proof of this fact is following exactly those same lines, okay? Now, then we proved Kahn's theorem, which I'm calling, you know, fundamental theorem indeed, that any separable II1 factor is AFD and thus isomorphic to the hyperfinite II1 factor R. So you have that this characterization of R intrinsic, you know, abstract characterization. R is the only amenable II1 factor. So R is amenable and it's the only amenable. So now this part is, I'm using Kahn's Fellner condition, which is in his paper, but the proof of this, that, you know, the way we went through it, went along to prove it, is not exactly his initial argument. This is a proof I found in the 80s. So from the local, from the Fellner condition, we proved a local approximate finite dimensional. You remember on a small corner that corner, you know, basically that support, infinitesimal support projection, commuting with the finitely many elements you want to approximate. Okay, it relied a lot on this black box sort of a result that we assumed. We did not prove. Perhaps we will prove it at some point, maybe tomorrow. And so with that we constructed from the almost invariant space, finite dimensional spaces H0, in M you construct an algebra, a small tiny algebra that's, you know, local, I call it, and you know, with the support almost commuting with the elements, and then, you know, you fill up the identity with such things by maximality argument, which works and can be carried on because everything is in Nord 2 and it adds up well, the estimates, because of the Pythagoras theorem. Okay, so we made these comments that, you know, I view this proof as much more natural. It's really, I think, you know, because of the parallel with the group case, because of many reasons. In the II1 factor context, it's, I believe, the natural proof. However, Kahn's initial proof, which is, you know, quite complicated and you know, I would say, you know, going through many more, you know, conceptual challenges, was very inspiring on the C-star algebra side, where, you know, for instance, it led to the proof that all groups are all amenable groups are quasi-diagonal, which I view as a fantastic theorem. Basically says that you have a Fellner type condition in the operator norm for the group. for C of gamma for the group for the left regular representation acting on the Hilbert space. Okay, so yeah, and then this is another page I failed to emphasize. So some consequences to Kahn's fundamental theorem. Let's get back to all those examples of amenable to one factors. So Kahn's theorem implies that for any countable ICC amenable group, we have L of gamma isomorphic to R. And that's obviously, non-trivial if you just take it as a phase problem, which is what the people were, trying to do in the 70s. What happens, I mean, you have this huge number of, the set of ICC amenable groups. I guess it's, it's unclassifiable. There are so many of them. It's not only it's a continuous family of such groups, but it's unclassifiably, in the sense that logicians give to that. So, and nevertheless, all their associated polynomial algebras are just R. Okay, it's many to one. This functor that takes gamma to L of gamma, at least in the amenable cases, all to one. It's just you have just one point, all of. Same for the group measure space to one factors, okay, arising from amenable groups. Okay, moreover, you remember that corollary, again, I get to that, when you take any cross product for Neumann algebra, B cross gamma will be amenable, so in particular B itself, you can take it to be R, and gamma an amenable, a countable amenable group, this cross product, B cross gamma, is R. Every time you just get R. For instance, you can take gamma on R, can act as a Bernoulli shift. You view R as that infinite tensor product of 2 by 2 matrices, but the infinitely many, you index them by gamma, and then you act on it by shifting the coordinates, again, the entries. So that is any group, in other words, any countable groups act on the hyperfinite one, as we will see, it acts outerly. So all those actions are not inner. Okay. Okay, and since any polynomial subalgebra of R is amenable, it follows that any to one subfactor of R is isomorphic to R. Okay. So in fact, one can refine this, and well, this solves, the issue of what are all the subfactors of R. So they are either n by n matrices or R, or isomorphic to R. Actually, this is their complete classification. It's, in fact, not hard to prove this result. I mean, just from the Kahn's theorem. So you have any B for Neumann subalgebra of R is a direct sum of n by n matrices tensor some abelian algebras, or if you prefer n by n matrices over some abelian algebras, direct sum of those, and then another piece that's of type II1, or what we say, which is the hyperfinite one tensor with some abelian. Okay, that's all of them are this one. Some of these can be zero, so n, any of these may be zero, of course not all of them. Okay, so, and by the way, this is the only one factor for which one could classify all its subalgebras. Okay, so, okay. Now, the next thing we wanted to do is to do a more subtle type of question. So, okay, we clarified what are all von Neumann subalgebras that as individuals, okay? So their isomorphism class is here, right? We classify them all. But the interest obviously is to, I mean, if you take a von Neumann subalgebra, it's more like, it's natural to look for the, rather than, you know, I mean, this is of interest. In our case, it's R. This is, of course, of interest. You take a subalgebra in another algebra and what this can be. But it's more interesting and obviously much more defined type of result to look at the iso class of the inclusion. So by that we mean, you know, two such inclusions are isomorphic if there is an isomorphism of the big algebras that carry the small one onto the other. And so, well, it's actually, you know, in this spirit is, actually that's exactly the reason for looking to these things, and especially in the case when B is a maximal abelian subalgebra of R, the Dixmier introduced this invariant called the normalizer. It's very natural, actually. So you look, given any subalgebra of M, of a II1 factor, you can take them also M in fact partial, you denote by N sub M of B the set of unitaries that normalize B. It's obviously a subgroup of the unitary group of M, and two special cases are these extremal situations. One, when, you know, you generate this unitary group is big, that is, you know, it generates, in the sense that it generates all M, one calls them regular von Neumann subalgebras, and the other case when you have nothing, except of course the unitaries in B, which always normalize, and those you call singular subalgebras. Okay, in the case of where B is a maximal abelian algebra, which was the case of interest for Dixmier actually, he introduced this in general though, that's nowadays called the Cartan subalgebra. Okay, and now it is immediate to see that the diagonal, you remember how much I stayed with that diagonal of R, is a Cartan subalgebra, because at each step you have the permutation unitary groups of on the diagonal that leave it that normalize it, but it also normalizes the future, I mean everything that happens after that from a step on. So what I mean so that unitary, for instance, group U0 that I was saying, you know, with just plus, minus, 1 and zeros, obviously normalizes D, okay? N generates all R, so that D is a Cartan subalgebra, and the fact that it's a massa is an exercise. Also, if this is something we mentioned before, right? If you have a group acting freely and ergodically on the probability measure space X, then this inclusion L infinity of X into the cross product by its cross product with gamma is clearly a Cartan subalgebra. So for instance, you have lots of examples like this, right? For instance, you take gamma, an arbitrary countable group, and you take the probability space to be the infinite product of a probability of a base probability space x0, okay, which gamma many times. You take x0 product with itself gamma many times, and let gamma act on these coordinates by shifting from the left. Okay, what one usually calls a Bernoulli reaction. Okay, so I wanted to emphasize all this because you see, there are lots of them. So you know, you take even, okay, so take gamma, any amenable group, take any free ergodic action of that gamma, specific gamma, for instance, any Bernoulli action. By the way, you can vary for that, you know, the base space, of course, and you get things with different entropies. So, you know, they are in some sense different up to conjugacy. They are different. Okay, and question is, you know, what about the corresponding inclusions? You have enormously many, besides this one we started with, okay? Here was the observation I kept from yesterday, this fact that, you know, the basic construction for a regular inclusion has some special properties, which I'm using in the proof of the next theorem, which is settling this question that I kind of, you know, implicitly posed on the previous page. What happens with all this Cartan subalgebra of the hyperfinite II1? So that's the subject of Kohn-Feldman-Weiss theorem. So which says that, actually, let me put it this way, I'm not even assuming the ambient factor to be the hyperfinite one. Anyway, we know that saying it's amenable means it's R. But let's put it in this form. So if M is a separable amenable to one factor, A is a Cartan, then A into M is isomorphic to this D into R. Okay? Now that says, so this is really Kohn-Feldman-Weiss, and it's in 81. Just a year before, Ornstein and Weiss proved this result, which seems like, you know, entirely ergodic theory. In any case, the, you know, formulation is ergodic theory, or, you know, in any case, it involves base space and, you know, measure space, points, etc. Not, you know, operator algebra kind of looking framework. So I'm claiming that this actually implies this part, which was already known from Ornstein and Weiss, that any two free ergodic PMP actions of any two countable amenable groups are orbit equivalent. I did not explain what that means. We come to that right away. So we proved this. This is what I proved, and this is the proof. That's where I needed for. It's for starting up this proof, for proving the appropriate. I mean, it was important to go through these pages of proof at the end of my lecture yesterday, because it's really identical to the proof of Kohn's theorem that we gave. And so, well, or rather to the way I did it yesterday. So that is, you first prove a Fellner type condition. That we proved by using this thing, you know, with the basic construction. So because you have to find this almost invariant projection, sort of finite rank. Actually, what we find is something that's finite rank over A. Okay, so it's like working in this basic construction algebra, okay, means that you do things relative to your subalgebra B, which in our case is the Cartan A. Okay, so this was a general thing. Okay, and so the Fellner type condition, actually I'm proving it in this generality. So if M is amenable and B in M is regular, okay, with the ambient being amenable, actually even less is necessary. It's a relative amenability that you really need here. Then you have this Fellner type condition, okay? So that was the first thing which proved being identical. You know, it's that same, the Han-Banach trick, I mean, or rather what we call Bayes trick. Then, you know, that gives you an almost invariant L1 function, and you pass to L2 through power Sturmer, and then with the constitutional distribution trick, and then, you know, that Namioka type Fubini interchanging, there is a T for which the spectral projection of this B which will be finite in the sense we want a finite-ish type of projection that's almost invariant in II. So that goes exactly the same way. And then through this kind of, local quantization type of reasoning, you get this little small piece that approximate your elements on a small corner with almost invariance to the given unitaries, what we call local AFD, and then from that through a maximality argument global AFD. Okay, so that's it. And so here we are. I want to explain the last how we can deduce that part with the orbit equivalence. So let's make the connection with orbit equivalence of actions from this purely operator algebra framework, which was we were talking just about Cartan subalgebras, okay? And so that's due to this observation of Singer, this first observation, which says that this is easy Singer, from Datia Singer, so his first years of mathematical career were in operator algebra. And he wrote several papers with Cadison, I think with other people also, and by himself. This is a paper by himself from 1955, after Dixmier's paper, which was very inspiring, this paper. And he noticed this, that if you have two group actions, actually, he did not quite put it this way, but it's absolutely all there, this observation it's a remark in his paper, and probably more important than the rest of the paper, this remark. So two group actions, say free ergodic, and we need them here, and countable, okay? Then the corresponding Cartan inclusions are isomorphic, in the sense, this is inclusion here. Okay, it's a misprint. So they are isomorphic in this sense, right? It's iso class of the inclusion. If and only if the two actions are orbit equivalent. That means that there exists an isomorphism of the probability measure spaces, taking, I did not emphasize by the measures, but this really, I mean, measure preserving with the inverse, etc. Almost everywhere, of course, we define this. I mean, we don't care about null spaces. Such that delta, the isomorphism, takes the orbits of gamma onto orbits of lambda, okay? For almost all t. It looks a little bit, disturbing, or I don't know how to say, you feel somewhat uncomfortable. You see immediately that, there is this almost everywhere thing. The orbits, wait a second, the orbits are countable, and I'm taking, well, the almost everywhere is for the t, okay? But except for those, null set, which, by the way, that null set, if you complete it through, it comes null set of t, which then, through gamma, a null set, take you then take the orbit of that null set, it's still a null set. And this is the key observation, okay? So that's actually why, you don't have to worry about this too much. And you see this, actually, this is really an exercise, okay? It's really just a remark, an exercise, that you have these two things. So, but you see, it's very nice, because, I mean, no matter how much one loves operator algebra framework, still it's beautiful that, this is equivalent to a statement that's about, points and actions and orbits and, things with the ground space being involved a lot, okay? Incidentally, look how neat this is compared to this. The operator algebra framework, I would say it's a bit superior, because you don't have to deal with the AE thing, you know, with the orbit equivalence, I'm sorry, with the almost everywhere thing, that just disappears, you know, in this. So, so it says that, okay, an isomorphism between L infinity spaces, you can view that way, extends to the phenomena, the cross product, if and only if it's orbit equivalent. You can view it this way. By the way, this isomorphism is not like there exists. This is delta extended. So if you go from right to left, it's this delta that implements this isomorphism. You extend it in a natural way. Okay, so the isomorphism you get here, it's restricted to L infinity of x is this delta. Okay, and vice versa, the isomorphism here restricted to L infinity of x, which we know there is a theorem of von Neumann, any such thing, isomorphism between L infinity spaces comes from a unique isomorphism of the ground spaces, it's that one. Okay, okay? So it's okay, so then of course this answers what we just said, you know, any two free PMP actions of countable amenable groups, since they give the same cartile, okay, they give orbit equivalent actions by Zinger's observation. Okay, and the second thing I wanted to say, yes, it's I wanted to emphasize how much stronger Kohn-Feldman-Weiss is, okay? So Kohn-Feldman-Weiss says much more than this, okay, than the orbit equivalence, than Ornstein-Weiss. Why? Because, in fact, you have other ways to construct Cartan subalgebras from group actions, which is this so-called, you know, I mean, it's another construction from group actions, which coincides with the initial one we took only when the action is free and ergodic. If so, then you get the same construction. So here is this other construction. So I am taking from the action, I forget about the group gamma. What I'm interested in is only the equivalence relation, the orbit equivalence relation. Okay? Which we view as defined modulo this equivalence, you know, with the, for almost all t, okay? So we can remove or put, you know, change the orbits of points in a null space of x, okay? And so the equivalence being is equivalent to s if they are one is in the orbit of the other, right? They generate the same orbit. Okay, so one associates to this it's like a groupoid von Neumann algebra of R. You can view this as a groupoid, obviously, you know, with little arrows, you know, corresponding to the equivalence between t and s. T goes to g. T is like with a little arrow, pointwise. So you do it like this. So very analog to the group von Neumann algebra. So it's the easiest way I did it. I choose. There are two ways to explain this, and I choose the way with the so-called local isomorphism, the pseudo group of local isomorphism implemented by R. Namely, I'm taking the set of all local isomorphisms, so this is X, and you know, you have the orbit equivalence, and you have local isomorphisms with you know, measurable subsets of X isomorphic to other, I mean, isomorphism between two subsets, measurable subsets, with the graph of this being included in R. So this is what I call the local isomorphism corresponding, associated with R. They form a pseudo group by just obvious composition. So the way you compose it with another one like that is, you know, that you just keep, you know, they cut off here and everything else, you ignore. So in an obvious kind of way, especially if you are an operator algebraist, this is very intuitive, because it's like multiplying two isometries, which obviously will give you, you just multiply them. And you take these formal sums with the coefficients in L infinity of x, okay, and again, this gives you an algebra with respect to this semi-group structure of multiplication of such local isomorphisms, composing them. And the trace here that I take is, I integrate, I take, so, I don't like v sub phi. I should have used u, like the canonical unitaries, except that these are like canonical partial isometries. I should have used u, not v. Anyway, let's leave it to that. U sub phi would be here, and for each such phi, I take the part of phi where phi is trivial. This is I of phi, so I of phi is the characteristic function of the subset of x for which phi is equal to the identity, okay? Each such local isomorphism might be on a piece, just the identity, and I take that marks the biggest, okay? And so I phi, so I'm taking A, the coefficient, times this characteristic function, and I integrate. This is a trace, it's very easy to see. And then you do exactly the same thing. You take the, you have an algebra, but you have also a Hilbert structure because of the trace. You take the completion of your algebra in that Hilbert, and that will give you the Hilbert space, and then you take left multiplication, etc., exactly like before. This is L of R. Now, there are, for instance, if you take the trivial action, so gamma may be a huge group, but it may act on X trivially. Every G, acts trivially. Then L of R is just L infinity of X. What this construction does, it's taking only the actual true action of gammas, the part that really acts, okay? If nothing, there is no action, okay, just the group, you just forget about the group disappears, it doesn't matter. While in the group measure space case, the group is always there, okay? So it's a completely different construction. They coincide obviously only when you have free ergodic actions. I mean, freeness is actually what matters. So one can do even more, okay? One can do a twist. So in this product, and this is the first time we do it, now we will do it more often in the second part of my lecture. You can twist it by a 2 cocycle. So this is why I feel terrible that this is not V, it should be U, okay? Because here is where I need V for this notation. So I can twist the product with the 2 cocycle like this. So when I multiply 2 partial isomorphisms, so lambda of phi, lambda of psi, I request that that's equal to V sub phi psi times lambda of phi psi, okay? So it's not just here in this untwisted version, this product is just this. Here I'm taking this to be twisted by V, which is will be a partial. I did not specify here, it's not only unitaries, it's partial isometries in A. So that means the range of the values it takes is partial isometry in an abelian algebra means what? You have a characteristic of support, and then on the support you have, like a unitary on that support. Okay? So you have this formula. Obviously V should satisfy some conditions which I did not write here because they are complicated. It's a 2 cocycle relation, but we'll get back to that. Okay, just believe me that you can have this twist. Okay, incidentally, you can do that even if you have your equivalence relation is from a free ergodic group action. You can take a very simple, the simplest 2 cocycle, it's a scalar 2 cocycle for the group. And groups, as we know, okay, have lots of 2, for instance, even this group, abelian group, z squared, you know, h 2 of z squared, this is non-trivial, it's equal to, I guess, z, right? Which, because it's like imposing that the 2 generators, you know, they don't, I'm sorry, this is t, what am I saying? So it's isomorphic to imposing that these 2, 0, 1 and 1, 0, they don't, they commute modulo scalar, okay, and the scalar can be anything on the torus. So this is, even this, you know, very simple group like z squared, so if you, in other words, if you have a z square action, free ergodic on the probability measure space, with this, any of these cocycles, will give you another cross product construction, a twisted cross product construction, okay? And my question is, obviously, this cocycle twisted cross product construction will still have L infinity of x as a Cartan subalgebra. And what's happening with these ones, the twisted ones, which suddenly we have a new class, okay? By the way, it's easy to see that, for instance, if I take the group to be amenable, like this one, z squared, acting, okay, with R being, you know, given by it, then it's still amenable, the II1 factor that you obtain, okay? But it's another Cartan. Well, by Kohn-Feldman-Weiss, it's actually the diagonal. So it means that this cocycle actually untwists, you know, disappears. It doesn't matter. Okay, so that's what I wanted to emphasize here, is that by the uniqueness of Cartan in R, we have that any 2 ergodic PMP actions of any 2 amenable groups on a non-atomic probability space are orbit, and that any 2 cocycle D for such actions is co-bounded. These are, you know, sort of mysterious, you know, kind of terms that I'm using. What does it mean to be a co-boundary? Well, you know, it's pretty obvious what it means, and, you know, so the okay, so this is one of the things I wanted to emphasize, but also, yes, I forgot to mention that this is given any Cartan. So now this is important, okay, and we'll keep that in mind. So, and this is, you remember, I started by saying, to see the answer about we need 2 remarks. So this is first remark, and I wanted to also, this is a remark by Feldman and Moore from 1977, so this generalized construction with the twisted version. And this is a theorem they proved, which is not that hard actually, namely that any Cartan inclusion is given by a countable equivalence relation with the cocycle through this construction. So in fact, you have, now this time it's really if and only. So any of this is a Cartan inclusion, and any Cartan inclusion comes this way, okay? So because of that, you have that the Kohn-Feldman-Weiss, you know, proves this, okay? So the equivalence of Cartan is equivalent to the equivalence of these pairs. So that means an isomorphism of x1 onto x2 that carries this relation onto the other, but also the 2 cocycle. So if this one is trivial, it's like saying that this untwists, because everything is isomorphic in the amenable case with the diagonal, where you have no twist, okay? Or any other of our examples where you have straight actions. Okay, so I guess we came to the, yeah, this is more like where I wanted to get at, you know, last lecture, but so there was quite a bit missing. Okay, so we resume after a break at, let's say at 2:10. We are here. Okay, so first of all, there is a name for sure that I missed to emphasize and actually also to tell a little story, which Masamichi kindly reminded me. And it's a pity not to say it, because it's, you know, UCLA related, and of course Masamichi and I come from, we are from UCLA, that's what we were. So the forgotten name is that of Henry Dye. So you see, there was between 1959 and 1963, quite independently of Izzy Zinger's remark, Henry Dye, so this was a few years after Henry Dye's observation and his work, I'm sorry, about after Zinger. So Izzy Zinger wrote his paper in 1955, and by the way, that was while he was on a tenure track at UCLA, okay? He had his first job at UCLA, and it's from there that he was hired at MIT, where he stayed, you know, the rest of his mathematical career. At that time, Henry Dye was a postdoc at USC. They were colleagues in Chicago. Both came to the Los Angeles area because both liked jazz, and apparently LA was a great place for, you know, listening to jazz music. And right, so anyway, they did not collaborate while being, you know, one at USC and UCLA the other. This was perhaps the last paper. Maybe Zinger wrote some other things, but they were backlog, I think. Like the genuinely last paper he wrote in operator algebra was this paper. Well, in 59 through 63, Henry Dye, even before he came to UCLA, so he was hired from Caltech, I'm sorry, from USC to UCLA on a tenure track, and then he stayed there, you know, throughout the rest of his life and his mathematical career. So between 59 and 63, he proved basically that all Cartan subalgebras of the hyperfinite one factor that come from free ergodic actions of abelian groups, okay, are orbit equivalent. You can say that, you know, in this language today, the way he formulated, he did not even assume you know, that this whole thing was happening in the hyperfinite one. If you want, what he proved is this, that if you take any free ergodic action of any abelian group, the cross product is isomorphic to R with the corresponding Cartan going to the diagonal. So anything like this is what he proved. Very important paper. So if gamma abelian, so if this is free ergodic, okay, then L infinity of x into L infinity of x, this inclusion is isomorphic to D into R. This is Henry Dye's theorem. So it's an important case, okay? Okay, so that's to be said. He did not actually work with orbit equivalence. He really did it this way. you know, with the local isomorphisms and working in the purely von Neumann algebra context. This is really his theorem. He never talks about orbit equivalence. Although, okay, as I said, you know, Zinger already had a paper about where he basically established that, you know, Cartan means the same thing as taking the, you know, orbit equivalence class of an action. So apparently Henry Dye did not like to work on the ground space. He really, you know, only liked to, you know, work with the, in the von Neumann context. So he immediately would switch to, you know, any kind of question like that to local isomorphisms, partial isometries, full group, something I did not even talk about. Okay, so that's like a little piece of history. And yes. And it was Henry Dye, by the way, who hired Masamichi. And Masamichi hired me. So it is a nice, you know, kind of story about that. So now next problem, obvious problem, is to look at all regular inclusions into R. Okay, so so let's look into this. So the Kornfeld-Weiss theorem shows that there exists just one Cartan subalgebra of R, right? Up to conjugacy by an automorphism of R. One would of course like to classify all regular inclusions, but I mean all regular inclusions, I mean there is some natural condition on B that you feel like imposing, and that's a sort of homogeneity, irreducibility kind of, you see, even for abelian, in the abelian case you require the Cartan are massas that are regular. So massa being a maximal abelian is a condition. I'm not only imposing that the normalizer generates R. After all, if I take here the scalars into R, that's of course like classifying R, which we know, I mean, we already settled the uniqueness as so, but you see what I mean? So it's, you feel like imposing some natural, that natural condition is this. You know, this is what I called homogeneity, reducibility condition. So for B to satisfy that its commutant, its centralizer in R is contained in B. So in other words, it's just the center of B. Of course, when B is abelian, this condition just says that it's maximal abelian, B. Now, besides the case B abelian, though, an obvious case of interest is when B is a factor. Okay, I generically denote that factor by n, you know, subfactor. By Korn's theorem, n, we know it's isomorphic to R. Okay, and the condition of irreducibility amounts to really being irreducible in this sense, you know, of having trivial relative commutant. Okay. So now, it is really an exercise to show, what did I do here? I probably wanted to put this on the next page, but with this, all this, it scared me off. I'll tell you what this theorem is. It is an easy exercise to show that if you have such an irreducible subfactor, which is regular, then if you take the normalizer and factor it by the unitary group of n, this quotient, obviously this is a normal subgroup in here. You take this quotient, I mean, you may ask, well, what topology? It's actually it's a nice Polish group, in fact, and it's a discrete group as a Polish group. But really, you can, it's discrete in a striking way. I'll get back to that a bit later on. Okay, it's a discrete group, this quotient. Let's call it the normalizing group of n into m. So it's gamma sub n into m. Generically we denote discrete groups with gamma in my lectures, and it will be countable if m is separable, and it will be amenable if and only if m is R. We'll get back to that, because anyway we will develop this, but let's answer this right away, this question here. That has been answered by Ogneanu. Actually, it's different the way he formulated, but it's equivalent to this statement. The irreducible regular inclusions N into R are completely classified up to conjugacy by an automorphism of R by the normalizing group, gamma. But this normalizing group, so the normalizer divided by UN. More precisely, and this is a pity here, it doesn't go on the next page, it's just that so how can I do this too? Okay, so here is what is, I'm sorry about this technical problem. I'll fix that by next time, of course, but now I need to say what I wanted to say. And that's the following. So this says it all, but of course we would like to be more specific. So what I mean by that, so is this, so if N0 into R is another irreducible regular, okay, then the initial one is isomorphic to this new one, if and only if its gamma normalizing groups are isomorphic. Which is obviously an amazing theorem, right? So it's completely classified by this normalizing group, okay? In particular, of course, you can take, you know, this is, so they are indexed by amenable groups, you know, any amenable group, so therefore, thus also, since all of them depend only on this, it's also isomorphic to this, for instance, to R, I'm sorry, to this N into, how should I, let me put it this way. It's isomorphic to this inclusion. I take R tensor product infinitesimal many times by gamma. So this is, say, let's call it gamma. Into R tensor product infinity many times gamma, tensor, I'm sorry, cross product with gamma. Okay, where this, actually, why don't I do it with the definition? I'm sorry about that. So I'm taking R to be, let's do it like that, and let's say that this action being the 2 by 2 matrices, tensor, infinite tensor product gamma many times, with gamma acting on it by shifting. Let me bring this up. Okay? So I'm taking a model such cross product inclusion given by the group gamma acting on R in this specific way. So anything you give me which has this gamma as normalizing group, okay, any regular subfactor with this gamma as a normalizing group, okay, is isomorphic to this specific inclusion, okay, where R is represented as we first define it as infinite tensor product of 2 by 2 matrices with the as indexed by the group gamma, and with the gamma acting on it by the Bernoulli action. Okay, so next what I want is to clarify this theorem. We'll say a few words about how one proves this. It's also in the spirit of what we've done before, but somewhat different. And the strategy goes back to Kohn, and who, by the way, so Kohn already proved this for gamma equals Z in 1975. And also for gamma finite. This was proved by Jones in 1980 in his thesis, for which Masamichi hired him at UCLA as a headrig for that thesis, by the way. And Ocneanu then, generalized it first, proved the KZ square, and then for all amenable. Now, there are different ways to prove this result. I'll say a few words about that at the right moment. Okay. Yes. So, I think I know what I've done. This was something I changed in the last moment to put this capital all, and then that ate me one line, and that pushed it here. And also produced probably all that mess. Sorry about that. Okay. So it may disappear the last line. So let's get deeper into this, okay? And it's clearly in the same spirit of theorem, should have, proof along the same lines, Fellner approximation, local, etc. You have to prove, though, here that, two actions, it's a non-commutative framework, so something will be, will have to change to deal with that. It's not quite the same. Here you see, first of all, I need to clarify this thing with the normalizer. There is a structure behind, and let's clarify first that. What I want to show you first is that such inclusions are really cross-product inclusions, okay? With not necessarily actions, but what one calls co-cycle actions. So I need to go through this. It's not a big deal. I hope you can, you won't feel uncomfortable about, it's lots of concepts here, but it's not a big deal. So what is a co-cycle action of a group on a threshold for Neumann algebra? That's just an action on B by automorphism, which preserve the trace. That's the meaning of when I'm saying it acts on something like that. Of course, it's a group morphism, but not entirely so. It's a group morphism modulo inner perturbations, okay? So more precisely, sigma G, sigma H is an add of V, G's H times sigma GH for some unitary elements which depend on two variables, right? This is the two co-cycle, and which satisfy this co-cycle relation, okay? You will see the necessity of this being satisfied. If I just, incidentally, if I take B to be a II1 factor, which is our case of interest, and action to be kind of free in some sense, which actually I'm explaining here, a co-cycle such action is free if sigma G is what one calls properly outer for any G different from the neutral element. An automorphism is properly outer if not even on a small piece is inner, okay? This something like an intertwiner by something in B of theta means that theta on a support of B is inner, and we don't even want that. It's like in the abelian case, it amounts to this automorphism not being the identity on any measurable set, okay? Which is what we call freeness, right, for an action. So if B is a factor, okay, then this amounts to theta being simply not inner, which is something we call outer, okay? So not inner is outer. Okay, so that's the case of interest for us. But I want this in this kind of generalized framework because I want to clarify a little bit also from the previous page. You remember in the, in the abelian case, we talked about two co-cycle, but never clarified what that is. Okay, so, the genuine actions, so what we usually call an action, corresponds, of course, to the case when V is 1. Okay, so you have just completely nothing here, right? Okay. Now, if you have a II1 factor and the action is free, you can immediately see that this second condition is almost redundant. The first one is already tells you everything. Well, actually, this implies that this holds true modulo scalars. But those scalars, it's a big thing, because that's like, you know, two cocycle scalar, and that may not be twistable. I mean, you may not be able to untwist that. So it's a deep subtlety here, and you know, we really want this condition, okay? Not modulo scalars, but really exactly this condition, okay? That's a cocycle action, okay? Where we require that. Why? Because this corresponds to exactly being able, I'll show you on the next page, but first let's give two remarkable examples of cocycle actions. So first of all, when you have a group already with a normal subgroup, okay, the quotient, right, you have, I'm sorry, so you have that the quotient acts on the right on the so you have the following. So if I take on the kernel, so you have the action of let's take this very concrete case. I'm taking the group gamma to be the free group with the generators in this set S, okay, and you take I'm sorry, so I'm taking a group gamma. I'm not emphasizing its relation, just the set of generators. So an infinite, an infinite group, but with generators, you know, finite or infinite. I need to give them a label, so I label them by this set S, and I'm taking the quotient, the map from Fs to gamma, which takes the generators of the free group on S generators onto the generators of gamma and the kernel. Now, the thing is that unless some pathologies happen, the kernel is F infinity, and this gives rise to this, you know, of course you have that L of gamma, I'm sorry, that L of care of this map. You know, this will be a subgroup. Care of pi sits in Fs. So L of that group, okay, is in L of Fs, okay, and it's normalized by F, by all the unitaries in Fs. So it is a regular subfactor. You can also see quite easily that it's irreducible, okay, in general, okay. In general, I mean, you have some pathological, but you know, you take just randomly any kind of situation like this, you have that. Okay, and the L of Fs, okay, you can, so this, your M is a cross product. It's exactly like writing the group Fs as the cross product of care of gamma of this group H with gamma. It's a cocycle relation because of course you lifted, you know, all elements for each element in the quotient, you lifted it up and multiply, you know, do the multiplications as automorphisms, that it will be modulo a defect from the subgroup. So you have a cocycle just there, you know. It's actually, of course, this is true whenever you have a quotient of a surjection from a group to another group with a kernel, but you will not necessarily have the irreducibility, etc., ICC condition. All these are automatic here, are very, very easy. So anyway, this is a remarkable, actually, two-cocycle situation. It's Kohn and Jones who use that. This is extremely difficult to untwist, so we'll keep that in mind. There is another one which is kind of cute. This is something I have introduced, the amplified cocycle. So what happens is this: you take a genuine action like a Bernoulli action, of the on the hyperfinite. So this is the interesting thing is that it happens, you know, you construct this out of any actual action on any II1 factor of any group. Okay, for instance, Bernoulli action on the hyperfinite. Okay, it's especially interesting when you for producing co-cycle actions on the hyperfinite one, because any group acts on the hyperfinite one. So take any action, gamma, free action of any group gamma on any II1 factor, and I'm now cutting with a projection the whole picture, okay? I'm taking a projection in N. P is equivalent to sigma G of P because, of course, the trace, I mean, you know, it's an automorphism preserves the trace. So say via this partial isometry, and then you take this, you see, so it's like perturbing sigma G by an inner thing. Obviously, okay, this, you know, it's kind of unique. I mean, of course, you have a choice here of Bg, and that's where, you know, the whole co-cycle comes from. So these guys, okay, on P and P, which is n to the T, where T is the trace of P, okay, give you a co-cycle action. And this is actually the co-cycle. So these are partial isometries, but you see right away that they end up, I mean, it's this product, this makes sense actually. This goes exactly into the range, the proper range is fit, okay? So this is a unitary in P and P, this, okay? It's a unitary in P and P. And obviously it's not clear at all you can untwist this. These are actually quite hard to untwist also. Okay, so both these are hard to untwist. So in fact, they do come in nature, very natural, you know, co-cycle actions. It's not like we, you know, invent them just for the sake of it. They come naturally, okay? They are as good as actual actions, and there is in fact, an important observation which we will do next before the hour, and which you know, makes them even more, shows even more that they are absolutely necessary to be discussed. So any co-cycle action, first of all, gives rise to a cross-product construction. So the same way we did it, you know, for instance, for the Cartan subalgebra, when we started to untwist it, you remember? I said that construction was due to Feldman-Moore. That was, it's simpler because it's abelian, but was a bit more sophisticated because you don't deal with actual true free action of a group, but rather with that equivalence relation. So it's an action by partial isometry, so like a pseudo group acting. So it's a co-cycle for that. So it involves partial isometries. Two co-cycle is with values in partial isometries. Here it's really, you know, with unitaries in a way it's a bit simpler because of that. So I'm defining from this action the cross product, which is a twisted cross product. So the product of two canonical unitaries now it's twisted by this V sub GH, and the way coefficients goes from the right side to the left side, though, it's exactly like before. So the only difference is this. This is the only difference. Of course, the star operation also gets, you know, I mean, the star operation, you will have to, you know, see carefully what that is. And there is also a notion of normalizing the two co-cycle. I don't want to get into that. It's too much algebra, okay? We don't want that. What is though clear is that B is regular in here, okay? I hope I'm convincing you enough. So if you want that axiom, you see this one? This is exactly what makes this cross-product algebra be associative. If I would have here this modulo scalar, okay, it will fail the associativity. UG times UH, everything times UK will not be equal to UG times UH times UK. That's where it intervenes, okay? So in order to have a cross-product construction with an associative algebra, which is a must in order for it to act on a Hilbert space, everything, of course, the operator algebra on B of H, it's an associative product, so we know we have to land on something associative, so from the real world, so to say, not something, weirdo. And that's exactly that cocycle relation. So one points this cross product, it's in the same way, it acts on those, with the formal series, with the Hilbert space, is that L2 of B tensor little L2 of gamma, but viewed as, direct sum of Hilbert spaces, L2 copies of L2 of B indexed by gamma, etc. That's the best way to view this algebra again, with as Fourier series, L2 summable for the Hilbert space, and L2 summable with that condition that they are convolvers for the elements in the cross product algebra. Okay, now one can prove very easily that the freeness, this is nice, freeness is equivalent to this condition. Okay, so you see this is again, something that comes, this condition is very natural. In particular, when you have the factorial case, that simply amounts to the irreducibility of n into its cross product with gamma, okay, into m equals n cross gamma. Okay, so it's a subfactor with trivial relative commutant in that case. Okay, and now this was the converse, which I am now we are kind of underlying this a bit more. If n is into m is irreducible and regular, and one denotes gamma this, then I'm choosing the UG. This is, yeah, UG in, this is this curly n, which is just the normalizer. So I'm choosing for each g in gamma a unitary in n, okay, from that class, and then I'm letting sigma g be out of UG, okay, and VGH this guy, which you can see from here that it will be something in n, okay. Well, this then m is n. This will be a cocycle. It satisfies trivially that cocycle relation, and m is n cross product with this gamma with respect to this cocycle action. It's a complete triviality, but the truth is that it was, pointed out. It's like, in a way, it's similar, but for II1 factors, like the whole story with the equivalence relation and the Zinger and so on, Feldman mode, those basic observations which now look like complete trivialities, but people took time to actually realize this thing. And now we need also this, when are these two cocycles, when are two cocycle actions equivalent? What is the proper equivalence relation? I mean, the appropriate sort of, the natural conjugacy relation between two such actions. When do we say that they are the same in some sense? Well, the natural equivalence of cocycle actions is the notion of cocycle conjugacy, which is kind of obvious. There exists so two are cocycle, if only if there exists an isomorphism of the ground spaces of the algebra BI. Notice that I'm not even taking the groups to be the same, and an isomorphism of the groups and the perturbations by unitaries in the landing the target algebra, such that first of all the two are intertwined, okay, modulo the identification of gamma 1 and gamma 2 via little gamma, okay, and with the co-cycle corresponding. So here it's not quite that theta of V1 is V2. Theta of V1 is this, by the way, this is a co-cycle for the sigma 2 that's equivalent, okay, as the obvious equivalence for co-cycles with the initial co-cycle. So after perturbing with the unitary, you see, obviously I missed to make this observation, but obviously if you have sigma g is a co-cycle action and you take any map like this, well, let's take it on Bi, okay, then add Bg composed with sigma g, so this sigma prime g is again a co-cycle action, and the co-cycle, say if this one, the co-cycle, if for sigma is v, the co-cycle for v prime for this guy is exactly that one. So v gh is vgh, which then, you know, I multiply left and right exactly in that style, okay? That's here I said it, but not here. So it's a conjugacy modulo of this perturbation, and that's how the two co-cycle will change. Sorry about that. Yes. Okay, so in other words, if say the two were actual actions, let's say to simplify things that V1 and V2 are trivial. What this says is the two actions are co-cycle conjugate if is exactly like Masaki was saying, if you have conjugacy of one with an inner perturbation of the other. Now that W necessarily will have to satisfy obviously some conditions in order for this to be a true action, which is implicit, but I mean they will follow. But if you just forget about the, you know, if sigma g is an action, it's an action, and you, after multiplying, if this is also action, then that implies that Vg sigma g of Vh is sigma g Vga. Actually, even that is modulo scalar, so there are roughly okay, so I don't think it's necessary to go too much into this, but of course not to make a mistake either. So here I'll change this for the next time. Let me see how much more I can tell you. Yes. So this is the thing for equivalence of co-cycle actions. Okay, it's the important missing thing which I had to remove because that was the thing I could not process, and I have to see where my mistake is somewhere in the text that I'm using. So there is a further observation by Jones, actually also by Sutherland, which you remember here we emphasized this thing, right? That any regular irreducible subfactor comes from a co-cycle cross product inclusion. Okay. Okay, so you have this, you know, automatically you have a cross product once you have a regular subfactor, okay, which is kind of nice, okay. Regular subfactors means classifying them is the same, or at least understanding them to understanding, you know, cross product inclusions. Therefore, the cross products, you know, in short, actually it's this that I was missing to make here, and which is this observation of Jones and Sutherland. It's separately, huh? So two New Zealandese who made the same observation at about the same time independently, and that is that you have that, so let's keep those notation, but instead of bi, I go to ni, because that's the case in which this is true. So this inclusion, so say this, I have a sigma 1 v1, I'm sorry, it's here. Let's just call it sigma 1, but it's sigma 1 v1, the action of gamma 1 on N1, and sigma 2 v2 is the other one action. So this is isomorphic. You would expect this. It's really like, you know, the observations of Zinger and Feldman-Moore, it's in that spirit. So this is if and only if these actions co-cycle conjugate to sigma 2 v2. Okay? So this is why I needed to tell you all this story, okay? So classifying inclusions like this, it's exactly the same as classifying co-cycle actions up to co-cycle conjugacy, okay? And actually that's what Ognanu did. Ognanu proved that up to co-cycle conjugacy there is just one co-cycle action of any given amenable group on the hyperfinite one factor, 3 ergodic, 3. Here we don't need, by the way, you notice that it's just freeness that was necessary for that, you know, to have that trivial relative commutant condition. All I need is freeness, because freeness implies that the relative commutant is contained in the subalgebra, but the subalgebra, it's the center of the algebra on which I act. But if that's a factor, it will be trivial, okay? So let's see, so automatically I have to talk a little bit about what does it mean to untwist a cocycle, or when it's a cocycle co-boundary, and that's because, you know, I like to understand when a cocycle action comes from an actual, it's an actual action. When I can perturb it by some WGs to become an actual action. So you say that you have the cocycle action of gamma on B untwist, or is a co-boundary if there exists a WG such that the cocycle, the two cocycle comes from as, you know, in other words, V is the derivative of W, right? It's okay, it's D of and so thus sigma V untwist if and only if it is cocycle conjugate to a genuine action, okay? You can put it that way. And I should say actually that this is a bit stronger than, in fact, than this. So you see, there is it comes all to that observation I was telling you about modular scalars. So this untwist, if it is cocycle conjugate to a genuine action, which is more than requiring that this is a genuine action. It means that plus, it actually means that these guys, you know, it's equivalent to saying that if I perturb the canonical unitaries, those UGs, in the cross product by this WG, this U prime G is a representation of the group. Okay, not add of U prime G's is a group morphism, but really U prime G. So that's where the scalar comes from. For instance, if you take any free group, in particular Z, but also any free group with n more than one generators, those have no, you know, cocycle actions, because you just individually, you know, make a choice for each generator, and that's it, you know. So there is no cocycle, two cocycle for actions. I mean, they may be stupidly because you have not pay attention, but if you just choose for each element, for each generator, an automorphism, and then you define all the others through products of this, words of that, then you get just a plain action of, a genuine action of Fn. And no, I'll stop here. Sorry. Thank you.